This is a brief introduction to a bipolar junction transistor. Before we get started, I want to just review the semiconductor materials and the PN junction that you might have learned about with diodes. And if you haven't learned about diodes, you might want to stop this video and go find a video on diodes first. But essentially, a semiconductor material is made of a certain type of element, for instance, silicon, that has 4 valence electrons, and it makes very stable covalent bonds and a nice crystalline structure. But what we'll do is we actually dope the material, meaning instead of having pure intrinsic silicon, we would actually add either pentavalent atoms or trivalent atoms in order to either increase the number of valence electrons or decrease the number of electrons to either more negatively or more positively enable that material to conduct electricity. So, for instance, a p-type material is one in which we dope this with trivalent atoms or elements that only have 3 electrons versus the silicon or germanium that has 4. And what that does is it causes an imbalance, a slight imbalance in the material. So we have this, it's going to be much more positively, it's going to have a lot more holes than electrons, is what I'm trying to say. So there are electrons, but those are the minority carriers, whereas the holes or the positive charges are the more majority carriers. And then an N-type material is the opposite. We would add to it impurities that have an extra valence electron, which would give us more of those potentially moving electrons in our material. Okay, and then so the majority carrier in the N-type material would be negative, and the minority would be the positive or holes. And so this is the basic formation of our diode, where we would have a p-type material on one side and an N-type material on the other. And those together would create this junction. We call this the PN junction, where those come together. Okay, so as also you might have learned that this would depend, the current here through this device would depend upon the external circuit. So what we could do is we could either forward bias this junction, this PN junction. We could reverse bias, so forward bias. We could reverse bias the junction, or we could apply no bias or a 0 bias. So no bias is pretty much what you see here. There is no voltage applied to the circuit, so there would be no movement of the electrons in this case. Now, if we forward bias, to forward bias this PN junction means we're going to apply a voltage with the positive terminal nearest the p-type material or the more positive material, and the negative side of the voltage supply to the more N-type material. So forward bias really just means positive to the p-type material, negative to the N-type material. And what happens here is, let's just look at the N-type material first. So the negative side of our voltage supply has an abundance of electrons. So as these electrons encounter this N-type material that is already has an abundance of electrons, we see that they tend to repel those electrons while while attracting the holes. And so they'll start to recombine with the holes, and these electrons start moving across this junction. Okay, we call this the depletion zone. Right here in the middle, there is a depletion zone or depletion area that will be somewhere around that junction. Okay, and it can be fairly large or fairly small. Again, it depends on how we bias this particular circuit. So again, so on the negative side, we're pushing those electrons through that depletion zone. On the positive side of the circuit, again, we are, the more positive charges we have out here, they are seeking to pull those electrons this way as well, and that creates that electron flow. Okay, so a couple things. Remember, electron flow is actually in the direction of the electrons. Now, I'm going to be speaking of conventional flow, and conventional flow is the opposite. It's where it's where we assume the current flows from positive to negative. So in this case, conventional flow would be in this direction, where the current would leave the positive terminal of the voltage source and return back to the negative. So it's exactly the opposite of the electron flow. But again, if you want to look physically at what's happening with those electrons, it does kind of help you see how that happens. So when we're in forward bias, that means that we have positive connected to the p-type material, negative connected to the n-type material, and the depletion zone is very small. A small depletion area or zone. So that actually allows us to establish that current flow through that junction. Okay, in reverse bias, let's look at what happens in the reverse bias. So reverse bias means that I'm going to have the positive lead of my power supply, my voltage supply, connected to the N-type of material and the negative connected to the P-type material. So for reverse bias, positive to N-type and negative to P-type. Now what happens here, again, if you just want to look at the electrons themselves, hopefully that's not too confusing since we're talking about conventional current. But let's just say we now have all these electrons that the p-type material is seeing, and we've got mostly positive charges here. So what that's going to do is it's going to repel those positive charges. It's going to repel the negative charges that we have in that p-type material, or the minority carriers, while keeping this p-type material very positive, because we're now going to start pulling all of those holes this way. And then on the n-type material, we have a more positive charge here. And so for the n-type material, we're going to pull all those electrons this direction, but that's going to repel the positive charges over here. So we're going to have more positive charges building up over here and negative charges building up over here that are going to recombine. And what this does is it creates a very wide depletion zone. Okay, so a wide depletion area. And it's going to be very difficult for any of the carrier or the majority carriers to cross that depletion zone. So essentially, that means that if we're trying to create current that's going from this N-type material through the P-type material and get back to our source, it's just not going to happen. Okay, so no current's going to flow through here. So for the reverse bias, I equals 0. Forward bias, we do have current. The current's going to flow from positive to negative. Again, that's the conventional current. And then, of course, with the no bias, there's no current there either, because we have to get past this depletion zone. Now, one thing I didn't mention was that when we are forward biasing this, and I'm going to redraw this as the forward bias condition. Lost some things there. I'm going to redraw this in the forward bias. So in the forward bias, we will allow current to flow through here so long as we can get past this depletion zone, and there is a small voltage associated with that. For silicon, that barrier potential is what we call it, is about 0.7 volts. So we need this to be at least 0.7 volts to turn on the diode, or to allow that current to flow from the positive back to the negative. Okay, so that's the diode and the PN junction that we've talked about. Now the bipolar junction transistor, a BJT for short, has two of these junctions. So we can either have two N-type materials which have a P-type material sandwiched between them, or we can have an N-type material sandwiched between two P-type materials. And that creates two junctions. We have one here, or one here, and one here. Okay, so the middle material, we call that the base of our transistor. Okay, so for the what we call the NPN, let me write that down here, the NPN transistor, that would be the P-type material in the middle. And for the PNP transistor, that would be the N-type material in the middle. Now, one side on the NPN transistor, one N-type material is called the emitter, and the other is called the collector. Now, these are not interchangeable. They're actually a little bit different. The N-type material for the emitter is more heavily doped, okay, whereas for the collector, it is more moderately doped, or lightly doped, we would say. Also, the base material is lightly doped as well. Okay, so what that means is we do inject impurities into those materials, but not as much as the emitter. Okay, so the emitter is the heavily doped side, and same thing for the PNP, the emitter and the collector. Okay, so let's talk about what happens with with these junctions, these PN junctions. So again, now we've got two junctions for each of our transistors, and we have to bias each one of those. So we could, what could we do? We could forward bias both of them, we could reverse bias both of them, or we could forward bias one while reverse biasing the other. Okay, so what are these junctions that we have? Let's identify those. First of all, The junction here between the base and the collector, that is the base collector junction. And then between the base and the emitter, that is the base emitter junction. Okay, same thing in the PNP, but I'm going to just work with the NPN for now. So let's say we decide that we're going to, I'm going to redraw one of these down here. I'm going to draw it a little differently this time. Let's put it on its side maybe. And I'm going to do the NPN. But let me just show you here, this P-type material, the base material here, is much, much, much thinner than the two N-type materials on the end. Okay, I'm going to call this the collector. This is, of course, the base. And this is the emitter. Now, this P material, let's say that this is the length of all three of these materials combined, whereas the length of the base is just the width or length of the base. If we want to call it width, you can call it width. But just to kind of show you, the length of the base is basically about about the length of the entire transistor is about 150 times the length of the base. So it's very, very small. So while this is a P-type material and it's doped with fewer electrons, making it a more positive material, it's very, very thin as well. And then the collector, of course, is doped with pentavalent atoms to make it a little more negative, but it's moderately doped or lightly doped, whereas for the emitter, lots more electrons here, because this is more heavily doped on this side. Okay, so let's say we're going to positively bias each side. Okay, so positive bias means that you have the positive side of your source connected to the P-type material over here, and the negative side of the source connected to the N-type material over here. And we're going to do the same thing on this side. So the positive side would be more positively doped, and the negative side would go to the N-type material at the emitter. All right. So if this is the case, and we're using the base here, what would that do? So first of all, again, positive, if this were a diode, we would expect to be creating current in this way from the base to the collector and the base to the emitter. However, keep in mind that the emitter is more heavily doped than the collector, and this P-type material is very, very thin. So there's not a lot of that positive charge there. So we're introducing the positive charge into this base, and what's actually going to happen is we're going to see all of these negative charges building up and dumping current basically into the collector. Okay, so all of these negative charges in the emitter coming toward the emitter, those are basically repelling all the negative charges in the emitter material and pushing those across, and they're going to just kind of take over and dump electrons into the collector. So what we're going to see here, again, in terms of conventional current, is that we're going to have a a lot of current kind of dumping this way through the entire transistor. And the problem with that is that it really doesn't matter what's going on at the base. Okay, so if we have a little bit of current at the base, it doesn't really matter what's going on there, because the circuit itself is kind of taken over and created this current that we can't really control very well anymore. And that's what we call a saturation. So saturation happens when both junctions are forward biased. Okay, and I'll draw you a graph in a minute just to kind of show you what that looks like. Now the other, we could also bias both of the junctions in the opposite direction, or the reverse bias. So reverse bias means we're putting the positive terminal to the N-type material and the negative to the P-type material. Negative to the P-type material, positive to the N-type material. Okay, so now what would that do? So again, we are now okay, I'll get it. So now we are we've got these positive charges here that are pulling the negative, or attracting the negative charges out. And we've got this positive material up here that is pulling our negative charges out this way. So what we're doing here when we reverse bias both is we're going to basically create a very large depletion region in the middle that's not going to allow current to flow at all. So at this case, and we're not going to have any current at the base. So that's what we call the cutoff region, is where both junctions are reverse bias. And all of this, it works for the PNP as well. It just, you would change around the voltage supply so that reverse bias just means that positive goes to the N-type material and negative goes to the P-type material. Okay, so there's one other operating area that we can look at. And that is, I'm going to just get rid of a lot of this now and fix it. Okay, and that is if we forward bias the base to the emitter side. Okay, so the positive side goes to the base and the negative side to the emitter. And we reverse bias the collector to the base. Now this is a slightly different configuration than what you're going to see going forward, but just want to kind of discuss what happens here. So at this point, the collector, we're going to have a buildup of these positive charges that's going to pull electrons to that side. And then at the emitter, we're going to see more of these negative charges that are going to repel those negative charges into the center. And as and depending on the size of of each of these sources, we're going to have some current going in at the base, and that's going to decrease that depletion zone so that it's much smaller. And these electrons are going to want to jump over that base, okay, because we've energized what's going on in the base. And so that's going to give us a nice controlled current through the transistor. And that's what we call the active or linear region. Where the base to emitter junction is forward biased, and the base to collector junction is reverse biased. Okay, so let's look at a graph and see what this really means. So we have this graph. We're going to look at the output or the operation of that transistor. And typically we look at it in terms of the voltage drop from the collector to the emitter, which we would see from here, VCE, voltage difference there. And we would also look at the collector current, okay? Which, if we're talking about conventional flow, remember the red marks that I made here, that was more electron flow, the direction of the electrons. But what we're actually looking at is that current, the conventional current, would flow from the collector to the emitter. Current would be coming in at the base as well. So that would be our base current, our collector current, and our emitter current here. So let's look at this graph. So this graph would, let me label it here. Let's say this is 5, 10, 15, 20. Let's say our IC, that's going to be in milliamps, where VCE is in volts. Let's say 1 milliamp, 2, 3. I'm just making this up as I go. So those are all in milliamps. So what we're going to do is we're going to see that, for instance, if our IB is, I should have drawn one below this, let's say 10 milliamps. And I'm going to draw another one a little bit lower, and we're going to call that IB at 0 microamps. So very small. So if we have IB of 10 microamps, maybe we have an IC of 1 milliamp. This is just for one particular transistor. It's not for every transistor. I'm just kind of making this one up. And this might be for IB is 20 microamps. And this would be maybe for IB is 30, and so on. You get the picture. So what we have here is that depending on the current at the base, right here, we would get a certain current at the collector that we would expect then to travel through the transistor. And so let's look at each of our conditions here. Now the cutoff, when both of our junctions are reverse bias, that occurs down here where we don't have enough of a base current to turn on the transistor. So we could have a voltage across the collector to emitter, but we're not going to have any current. So that's going to be right around at IC equals 0 milliamps, or a very small amount of leakage current, but it's not enough current to really turn on the transistor. And then when both junctions are forward biased, we don't have a voltage drop across our collector to our emitter side. So that's going to occur somewhere right in here where we have a good bit of current but no real difference in voltage across the transistor. So that's our saturation area. Okay, so this is saturation, and this is cutoff here. And what that leaves us in the middle, let me change up the color a little bit, is that this is going to now be our linear or active operation area of our transistor. Okay, so this is the linear or active region. And what you notice is it's fairly linear in the sense that a particular base current leads to a particular collector current. And that's what we call the beta of the transistor. So the beta, the DC beta, is actually the ratio of the collector current to the base current. And typically this would be somewhere on the order of 100. So maybe anywhere from 50 up to about 500 could be the beta. So it's literally whatever the base current is times that beta will give you the collector current. And that's, each transistor is created with a particular beta in mind. And that's done by controlling the actual doping of the N and P and N type materials there. Okay, and that's what we want for the active and linear region. Okay, so saturation and cutoff might be used when you're using your transistor as a switch. You want it to basically operate as on or off. However, when we use the transistor as an amplifier, we want it to operate in this linear or active region because we can control the output. Also, we want to operate in such a way that we don't enter the saturation or the cutoff region accidentally, because at that point we wouldn't get the output that we're expecting to have. Okay, so let's go back to some equations here. The beta, again, is the ratio of collector current to the base current, IC to IB, which means that IC is just beta times IB, or of course IB is IC divided by beta. Okay, so those are the relationships there. Again, this is in the active region only, the active area or active region, or linear region. All of those names apply. That's where this is true. If we enter the saturation, of course, it's not going to be true anymore. That's where we have that unbounded current. Well, we'll have a maximum saturation current. We'll talk about that in a minute, dependent upon the circuit. But it's pretty much the maximum current we would expect to see, and we wouldn't get any more current and no voltage drop across the collector and the base. Okay, so what does all this mean in terms of our circuit? Okay, so let's draw, first of all, let's go back up to our NPN and our PNP and draw the circuit symbol for each of these. So for the NPN, the circuit symbol, we have the base, which looks like kind of the base of the element here, or the component. And then there's an arrow at the emitter side of the transistor. And the emitter side, the arrow indicates the direction of conventional current. So that tells us that IE would be flowing out of the emitter side, which again shows that our collector current should be coming in IC, and IB would be coming in. Okay, so the way to remember this, where this arrow is here, is that that arrow is not pointing, I'm having trouble spelling, not pointing in. Okay, so NPN, okay. For the PNP transistor, it's exactly the same as far as the base and the collector. However, the arrow is actually pointing in from the emitter to the base. And that we would say is pointing in, okay? So starts with a P, pointing in. I don't have another P that I can show you. But for that, the conventional current, IE, is coming into the transistor. The collector current would be leaving, IC, and IB would be leaving as well. Okay, so let's go down and actually draw a circuit and put some of, and do an example and see how this works. So here's our, I'm going to use an NPN transistor. And I'm going to add a resistor and a biasing voltage to each side. And here's my base. I'm going to add a resistor to the base. And this is a common configuration of an amplifier circuit called the common emitter circuit, because the emitter is common to both what we would call the input side and the output side. And they're all connected by ground. So on the base side, I'm going to add a voltage. We're going to call that VBB, showing that it's applied at the base. We're going to have a resistor at the base. I'm going to call that RB. And then on the collector side, because remember, this is the base, this is the emitter, and this is the collector. I'm going to have a resistor at the collector and a voltage applied at the collector that is called VCC. So again, for collector. Notice I have my positive terminal of the VBB connected to what is the P-type material. Remember, this is the NPN. It's not pointing in. So we've got the not N, P, and N type collector current here. So I've got the positive, the base to emitter side is forward biased, where the collector side has the positive going into the N-type material, so it's reverse biased. And let's just see what happens with this. So I have it working in what should be the active region or linear region, active region. And let's just say that the transistor has a beta. You would need to know this. The transistor has a beta of 150. That means that, now let me just mention the beta real quickly. Again, the beta is the ratio of IC to IB, and what we call that is the current gain of the transistor. So how much, if you put in 10 microamps into the base, and you would get out 150 times that, or 1.5 milliamps of collector current. Okay, so that's the current gain. On your data sheet, you might also see it referred to as HFE. And that name is the hybrid forward current common emitter. So you don't need to worry about all that, but it is also the current gain, which is the beta. Okay, so if you see that, and we call that the DC beta because it's referring to the DC current gain, and AC will come later. But again, the HFE is also the same thing as the beta. So a few other things that I want to note. Again, with the direction of this arrow, we have IE leaving the transistor, where IC is going to be coming in. Again, think of this source. It's wanting to create a current coming from the positive terminal back to the negative. And the same thing with the voltage at the base. And so that's going to be your IB. So if we were to just kind of take a look at, let me get us a little network in there. So in this network here, you see that we have IC coming into this box. Forget about what's in the box. It doesn't matter right now. We have IB coming into the box, and we have IE leaving the box. Now, we know from Kirchhoff's current law that the currents coming in to any node or any junction have to equal the currents leaving that same area. So if IC and IB are coming in and IE is leaving, IC plus IB have to equal IE. And that is going to be the case. So keep that in mind. That always should be the case. Also keep in mind that if IC is really the same thing as beta times IB, we could actually substitute that in for IC. Then beta times IB plus IB would equal IE. And if I pull IB out of both of these terms here, I'm left with beta plus 1. Think of that as I'm dividing this term by IB, that would leave beta. I'm dividing this term by IB, that would leave 1, and that would be my IE. So IE would be IB times beta plus 1. Now in this case, beta is 150, right? So it's very large. So how much larger is 150 times IB versus 151 times IB? It's not very much different. So IE is going to be pretty much the same as IC for any beta that's much, much greater than 1. So if it's in the hundreds, it's pretty much the same thing. But if you want to be exact about it, you could use that as well. Okay, so let's figure out what we've got here. So beta is 150. I'm going to plug in some numbers just to make this a little easier here. We've got 5 volts that we're applying at VBB. We've got 10 volts over here. RC is going to be 100 ohms, and RB is going to be 10 kiloohms. Okay, so let's just go ahead and find all of the currents and the voltages here using these numbers. Okay, a couple things to note. First of all, there is some barrier potential here from the base to the emitter. We would need to get past in order to turn the transistor on. So we need some current through there that's going to give us a drop of at least 0.6 or 0.7 volts. Some texts say 0.6, some say 0.7. We're just going to use 0.7 for this. So let's figure out what that means. So at E down here, at point E, the voltage at point E with respect to ground is simply 0 volts. Now, why is that? That's because our emitter is connected straight to ground. So we look at this as our reference voltage where V is equal to 0, and then that is connected straight to the emitter. So it has to be the same voltage. So VE is 0. Now the voltage at B, we would see this rise of 0.7 from the emitter to the base. So that would be whatever VE is plus that 0.7. And if VE is 0, that means we have about 0.7 volts at this point B right here. Okay, so now let's figure out what our IB is. So IB is going to be whatever the voltage we're applying is minus the voltage at B divided by that resistor. I'm sorry, RB, not RC. So if we're applying 5 volts at VBB and we have 0.7 volts on the other side of our 10K ohm resistor, then we should be able to use Ohm's law to figure this out, which would give us about 430 microamps. So that might sound like a lot, but it's really not, because remember, our beta is 150. So that tells us that IC, which is beta times IB, would, if we're acting in that linear region, which we are trying to do, that would be 150 times that 430 microamps, which would be about 64.5 milliamps. Now IE, a couple ways you could look at IE. That's going to be IC plus IB. It's also IB times beta plus 1. So either of those equations are fine. So 430 microamps of IB plus 64.5 milliamps IC. I'm going to use my calculator here. Gives us about 64.9 milliamps for IE. Now notice the difference between IC and IE is about 0.4 milliamps. And when both of those are starting out as 64 milliamps, that's really small. So IE and IC are pretty close to the same. Now the only thing we don't know is VC and VCE. So the voltage at C is going to be the voltage that we're applying at VCC minus whatever the voltage drop is across RC. So I know the voltage on one side, but I don't know the voltage on the other. But I do know IC now. And IC times RC will give me that voltage drop from Ohm's law. So we've got 10 volts that we're applying at VCC minus the 64.5 milliamps times the 100 ohm resistance of RC. And that means that we have about 3.55 volts at VC. Now, again, you always want to know where you are in terms of your voltage drop across the transistor from the collector to the emitter. So VCE is defined as the voltage at the collector minus the voltage at the emitter. So if we have 3.55 volts at the collector, and again, we have 0 volts at the emitter, the drop across there is 3.55 volts. So how do we know we're operating in the linear region? Well, that's going to depend on our IC and our VCE. First of all, if we're in saturation, that means that VCE would equal 0. Okay, and we know that that's not true. VCE would have to be somewhere above 0.2 to make sure that our transistor is actually on, okay, and not in saturation. So if VCE was 0, that would tell us we're in saturation, and we're clearly not because there is some voltage there. Now, what would the saturation current be? The saturation current, remember, if VCE was 0, that means that at VC we would have 0 volts. So the saturation current, which we would call IC sat, would be the case where our VCC for this circuit divided by RC, that would give us 10 volts divided by 100 ohms, or the saturation current would be 100 milliamps. Okay, so we already see that our IC is a good bit smaller than the 100 milliamps that we would expect to see if we were in saturation. That would be the max that you would see. Okay, so what about cutoff? Well, cutoff would be whenever IB is 0, but what would that make our VCE? Well, cutoff basically means the transistor is open and not working, or off if you want to think of it as a switch. So that means that VCE would equal whatever that VCC is that we're applying at the collector, and that's not happening. And we would also see an IC of 0. So when we see that our VCE is well under the cutoff voltage, and we see that our IC is well under the IC saturation, we see that we are operating in the active or linear region for this BJT. Okay, I will post more videos with some extra problems to work, but hopefully that gives you a good idea of the basics of a BJT transistor.